All right, our second kind of improper integrals happen when there is an infinite discontinuity someplace in between our closed interval. There's some sort of vertical asymptote. All right, and that could be on the left side, could be on the right side, or it could be someplace in between here. So let's say that our function f is continuous on the interval. It's closed at a, it's open at b. It's open at b because there's an infinite discontinuity at b. And so here's what the improper integral would look like. It's improper, but it's in disguise. Like, you don't know because a and b are just numbers, and you have some sort of function with respect to x. We're going to turn that into a limit just like we did before, but we're going to take that b value out, replace it with something. It could be a c. You could replace it with, whatever that, some sort of variable, as long as it's not one that's already being used. And then we're going to approach that original b value from the left. In order to understand that, let's take a look at a picture here. So we have on the right-hand side, this infinite discontinuity. We have a vertical asymptote there, and we're going to approach it like if we have a vertical asymptote on the right-hand side, we have to approach that from the left, which is why this limit has c approaching b from the left-hand side, because I have to approach it from the left-hand side, okay? So once I've turned it into the limit, this one-sided limit, then I can evaluate the definite integral and then perform the limit. If the limit exists, we'll say that it converges just like on the previous ones, and we're going to say that it diverges otherwise. It's going to go shoot off to infinity, okay? Our next case is if we have an infinite discontinuity on the left-hand side at a, right? So we have a vertical asymptote at a. We're going to turn that into a limit. Again, it's in disguise. We're going to take the a out, replace it with something, and then have that something, let's say c, approach a from the right-hand side this time. So again, let's look at a graph to help us make sense of this. That if I have a vertical asymptote on the left-hand side, on my lower bound, then I have to approach that thing from the right side of that thing, which is why it's c approaching a from the right. We're going to say it converges if that limit exists, and we're going to say that it diverges otherwise. Okay, and then our third and final case is that there is an infinite discontinuity. There is a vertical asymptote someplace in between a and b, and this one is probably the least obvious one. Well, in this case, you need to break it up at that infinite discontinuity, turn it into two separate integrals, both of which are improper, and then you're going to perform these previous ones on the left side and on the right side. One like that and one like this. Okay, so here's a graph of that thing happening. We have this infinite discontinuity here at c. So I'm going to break this up. At c, perform the definite integral, or the limit, as we approach c from the left-hand side, separately as approaching it from the right-hand side. All right, so I think that this one will make a little bit more sense if I put some numbers in here so we can see how this thing is actually going to play out. All right, so let me scroll down to the one that we just did right here. Okay, so let's just say for the example that we're working with here that this is the number 1, this is the number 2, and this is the number 3. And it would not have been obvious without doing some sort of investigation that we would have had an improper integral. It would have looked originally like this. The definite integral from 1 to 3 of some sort of function with respect to x. Okay, without some sort of investigation, I wouldn't have known that it was improper. Oh, I see the graph. It does have a vertical asymptote right here at 2, so I need to break this up as two separate integrals. I'm going to break it up from 1 to 2 of f of x dx plus the definite integral from 2 to 3 of f of x dx. Both of these things are improper. If I look at this one on the left-hand side, it's improper. It's got a upper bound, which has a vertical asymptote, and then the second one has a lower bound, which has an asymptote. Okay, and then whenever I go to set up the limits for each one of these things, one on the left-hand side would be the limit as, and what I tend to do is if it's the bottom one, I replace it with an a. If it's the top one, I replace it with, let's say, a b. So I'm going to say the limit as b goes to 2, and this is this one that the vertical asymptote is on the right-hand side of it. So I am going to approach that thing from the left, which is the negative side. So approaches 2 from the left of the definite integral from 1 to b of f of x dx. Plus, and now the second one here, also going to turn that into a limit, but this time I'm going to use an a. It's on the lower side there. 2 from the, okay, so on this side, we have the vertical asymptote is on the left-hand side, but in order to approach it, I have to approach it from the right. So this will have a little plus sign on it. Definite integral from a to 3 of f of x dx. And then we take the antiderivatives of each of those things, apply fundamental theorem of calculus to it, and then finally take the one-sided limit for each one of those. Okay, so now we're going to take a look at an example of one of these. I've got to evaluate definite integral from 0 to 1 of 1 over the cube root of x with respect to x. So it's not immediately obvious that this one is improper. Why is this one improper? Well, the reason why it's improper is because for the function 1 over the cube root of x, it has a vertical asymptote right here at 0. As a matter of fact, here's a graph of this happening, right? If we were to take that lower limit of integration, plug it in 0, it'd be undefined. We'd be dividing by 0. We've got a vertical asymptote here. And notice how it does seem to collapse to that y-axis pretty quickly. Might be a pretty good indication that this limit is actually going to exist. So let's give it a try. So again, I'm going to replace, I'm going to turn this thing into a limit, specifically a one-sided limit. And we need to approach that 0 from the right-hand side, so from the positive side. So this is example something, example 6. And we're trying to evaluate the definite integral from 0 to 1 over the cube root of x dx. And we're saying what makes this thing improper is that we have ourselves a vertical asymptote here. Vertical asymptote, so we need to turn this thing into a limit, which makes this thing improper. Okay. So we'll turn it into a limit. We're going to get rid of the 0. It's on the lower side. I'll just go ahead and replace it with an a. We're going to approach 0, and as we said, we need to approach that from the right-hand side, of 0. So put a plus sign in there. Definite integral from a to 1, and then I'll rewrite this as x to the negative 1/3 with respect to x. All right, ignore the limit for right now. Pretend it doesn't exist, but go ahead and write it down again. And evaluate, take the antiderivative of x to the negative 1/3 power. So I'd add 1 to the exponent. That would be x to the 2/3. Divide by 2/3, which is the same thing as multiplying by 3/2. And then we're going to evaluate that from a to 1. All right, still we're not at the point where we're going to evaluate the limit. Just bring it down. And then we'll go ahead and plug in our 1 and our a. So 1 to the 2/3 power minus a to the 2/3 power. Now we're ready. Now we're ready to take the limit. Now remember that for the most part, the plus sign on the 0 are notational reasons. Like it doesn't even make sense on the left-hand side. Usually limits are supposed to approach from both sides. This one's only on the right-hand side. So as far as evaluating the limit, we still just plug in 0. It doesn't matter if it had a plus or a negative sign in there. We still just plug in 0 and see what's going to happen, because sometimes everything works out just fine. All right, so the first part of this, 1 to the 2/3 power, is still just 1. So I have 3 over 2. I got 3/2. And then on the second one here, when I take 0 from the right to the 2/3 power, it's still 0. It's gone. So that part is finished. It's been eliminated, and there's our final answer. So we're going to say that our definite integral here converges to 3/2. And again, the graphical evidence here seems to point towards the fact that it collapses to the axis quick enough that it actually does converges to 3/2. Let's take a look at another one here. Evaluate definite integral from 0 to 2, dx over x to the third. Why is this one improper? Why is it in this lesson? Again, the reason why is because we have a 0. If we had a 0 down in the denominator, we've got another vertical asymptote, and here's a graph for this one. All right, now on this one, notice how far away that graph is from the y-axis. This one doesn't look like it gets there quick enough. It gets down to the x-axis pretty quick, but that's not where we're taking the limit. We're taking the limit towards 0 here, right? Okay, so let's give this one a try. It seems that the evidence is pointing towards this one not actually working. So I'm going to actually do a little bit of coloring here because I wanna. So it's all of this region here underneath this curve. And this, I mean, it's perfect, right? It's like it came colored. All right, that's what I'm trying to find the area of. See if it's unbounded. I'm going to take the limit. And since the vertical asymptote here is at 0, we're going to approach that, just like we did before, from the right-hand side. So for this example, 7, I've got the definite integral from 0 to 2 dx over x cubed. We're going to take out, and well, yeah, notice, of course, that we've got an improper integral because we've got a vertical asymptote, which makes it improper. Doop. Make it a limit. Limit as a approaches 0, as we said, from the right-hand side, plus definite integral from a to 2, and then I'll rewrite this as x to the negative third power. Now we're ready to evaluate the definite integral part of this. Let's say add 1 to the exponent would be x to the negative 2 divided by negative 2. I'm going to evaluate that from a to 2. And maybe do a little bit of rewriting here. I'll just take out this negative 1/2 here. Or, x to the negative 2. Okay, again, from a to 2. Now we're ready to evaluate it FTC style. Negative 1 over 2 squared. 2 squared is 4 times 2 is an eighth. So negative an eighth. And then minus a negative, which makes it plus. And we would have 1 over 2a squared. Okay, now we can do the limit. All right, on the first part, negative 1 over 8 is not affected. But over here on the right-hand part, this one, when I stick 0 down in the denominator, I'm dividing by 0. This should go to positive or negative infinity. Which one is it? As if it actually matters. It does matter. The number's going to be positive. Doesn't even matter whatever I'm sticking in here. This number is going to be positive. So this is going to tend towards positive infinity. So this one is infinity, which means that this area diverges. As x gets closer and closer to 0, this area is getting bigger and bigger and bigger, infinitely big. All right, it looks like this is the same exact graph, but now we're going from negative 1 to 2. From negative 1 to 2, how does that change this problem? All right, I want to do some more coloring here. So we're going from negative 1 to positive 2. So still this piece over here. And Then we also have this piece that's over here on the left-hand side. All right, so I'm going to pretend I'm going to play like I haven't already done this problem, where the right-hand side we already know diverged. But remember, there was something that we stated right up here. Diverges if any part diverges. The thing that's in the box right there, that's going to come into play, as we're going to see in just a moment. Okay, so if this problem was all by itself, I may not have known that, right? So I'm just going to go ahead and play like I'm completely devoid of that knowledge. So example, what is this? 8. And this time we're taking the definite integral from -1 to 2 dx over x to the third. Okay, so here's one where we have an asymptote that's in the middle of our the interval that we're working with. It's right here at 0. So for this particular example, we do have to break it up. Before we take limits and stuff, we have to break it up as 2 separate integrals. One that's going to approach 0 from the left-hand side, and one that's going to approach 0 from the right-hand side. So this should be equal to the definite integral from -1 to 0 dx over x cubed plus the definite integral from 0 to 2 dx over x cubed. And now I can pretty much conclude that I'm done here. And the reason why is because we've already shown that this part here diverges. By example 7, I think it was. Anyway, so since this portion of it diverges, I'm going to say the whole entire problem diverges. And that one's finished, right? I mean, it makes sense. This part was already infinitely big, so the whole thing is still infinitely big.